Hello everyone. Today we will discuss the construction radio and then the RF signal in the tunnel propagation loss. Before we start the discuss the details of the calculation of tunnel propagation loss, you guys may use the IB Wave or WinProp or other tools before for indoor coverage. Yes, you can use IB Wave, WinProp or others to calculate the propagation loss in the tunnel. But it's quite the time consuming because I used these tools before. You need to do a lot of things. You need to put the materials. You need to do all these constructions, the tunnel size, the shape, all this is very time consuming. And then on the other hand, in some cases you just don't have the tool. Maybe your organization hasn't purchased the tools yet, so it's good to have some of estimation, a quick estimation way to get the tunnel propagation loss. First of all, let's see what is a construction radio. The so-called construction radio maybe is not a standard industry terminology. I just use a construction radio here is to for a dedicated land mobile radio system. This land mobile radio system is used to support the construction site for voice communication between key personnel. That time when I supported this project, it was about 15 years ago. The LMR didn't support the data service yet, but now the new generation LMR can provide the data service. And in this project, it facilitates direct communication between the project managers located in the above ground office and then the supervisors working inside the under construction subway tunnel. Because you know the very early stage, the subway tunnel is just with concrete walls. There's nothing inside. Then you need to put all this like leaky cable for telco system, for intercom system. You need to put all these tracks, all these and the signal systems also. So this system also allows the supervisors in the tunnel to coordinate with the team leaders. These team leaders positioned at a different location within the tunnel, including various station platforms. This communication network is critical for ensuring safety, efficient coordination, and then timely decision making in a challenging and then confined underground environment. This one is the schematic diagram of the construction radio system. It is not clear for you to see here, and this is I did this on purpose, just some kind of confidential information I cannot release here. But you can see the idea is, okay, this is above ground office, the project managers, the few projects, so different project managers, they may be in the office here or somewhere other places. They need to talk to the supervisors in the tunnel, all this tunnel, all these stations, platforms, and the people inside, the team leaders, the supervisors, they also need to talk to each other. So this construction radio is for this purpose. This is just a schematic diagram. And then in this tunnel, we need to calculate the propagation loss. This is critical because some story behind this project before I joined to support this project. They actually have some of doubts, and then the understanding the time in the team is in the tunnel, the land mobile radio system can only transmit about 100 meter. So they need many base stations or repeaters in the tunnel. So this is far over the budget. So when I joined, I did a calculation. That time I used a waveguide to calculate the tunnel loss, and then of course did some of leave a lot of margin. So the conclusion I give the team that time was can cover at least 1 kilometer. So okay, the team they believed me, and then they used this one to tender for the project, and then won. And of course, we installed and we implemented this project successfully also. So now I just summarize all these put together. So if you guys have a chance to support construction radio, I understand now a lot of construction is going on for digging tunnel, building subway all around the world. So you should have a lot of chance to support this kind of similar project. So this is the baseline for you to take a reference to do the calculation. So this is a simplified formula to calculate the tunnel propagation loss. And then, okay, for me, the K is a constant. It depends on the material, whatever. But for copper, it's 4.34. So for tunnel, I just simplify this K to 43 times 10 here. Do the calculation. And then this is quite accurate. I have some test result compare with the calculation. I show you guys later. So here are some of the calculated results. So this is the tunnel propagation loss after 300 meters. Because the loss inside 300 meter to the transmitter, we can't calculate this way. It is not accurate. But anyway, the propagation loss in 300 meter is not the calculation is not important because the signal is always strong enough for your receiver. So you see K, we put 43 here. A is the width of the tunnel, and B is the height of the tunnel. And then the frequency, we put 150 megahertz, 300 megahertz, 450 megahertz, and then all the way to 980 megahertz. So you see for 450 megahertz, the propagation loss per 100 meter is 4.25 after 300. So this one we can calculate this way, and then this calculation actually is quite accurate. We can see from the next slides because I did some of the tests. So here are some of the calculation results. I searched a lot of papers and resources back to 15 years ago to get this table here. Of course, I lost all these links, but the summarization is still here. So you see for the first 300 meters, the propagation loss, the highest one is 150 megahertz. Because you understandable, the lower the frequency, the longer the wavelength, then compared to the size of the tunnel, it's less space for the radio wave to propagate in the tunnel. So 300 meter for 150 megahertz radio frequency, the loss is 120 dB, quite high. And then for 450 megahertz RF signal, the first 300 meter loss is 85 dB. And then after 300 meters, per 100 meter loss is 4.2 dB for 450 megahertz RF signal. And then the total loss for 1 kilometer for 450 megahertz is 115 dB. We use this value to calculate the loss in the tunnel. And then we also have some of test result. We can compare it, and then this calculation based on this table is quite accurate. Let's see in the tunnel. So this is the tunnel. We set up the test. So here is the transmitter, transmit the RF signal, at 450 megahertz with Yagi antenna, and then the tunnel is both sides here. Then we tested in all these locations, but we pay a special attention on C and E. You see, C is almost 1 kilometer away from the base station. Actually, it's 810 meter, and the E is 1.275. Is almost 1.3 kilometer away from the transmitter, and then the received signal tested and then calculated. So here you can see the calculated RF signal strength at the point location C, supposed to be minus 57 dBm, and then the measured value is minus 61 dBm. The calculated value at the E is minus 78 dBm, and the measured value is minus 87 dBm. So the difference here is 6 dB, and here is 4 dB. So this is considered quite accurate. As you know, in RF coverage simulation, we always have some of margin. For example, if you like to have 90% of reliability, you need to at least 8 dB margin. And if you want to increase the reliability from 90% to 99%, you add one more 9 here. Then you need to add one more 10 dB here. So the margin will be 18 dB. And similarly, if you want 99.9% reliability, you need 28 dB margin here. This is quite a common standard use case in our RF coverage simulation. And then this is all for today. Thank you. If you like to have some of detailed discussion, or you have some topic like me to prepare, please drop me an email at thinkingknife@gmail.com. If you like this video, please subscribe and like and share. Thank you.